In this video, we're going to talk about describing quantitative data by measuring center. So there are two big ideas when we talk about the center of data. One is the mean. Now, I'm sure you've heard of the mean. We represent that in statistics with this thing that is an X with a bar on top, literally pronounced X bar. So that's a distribution of quantitative data, and it's the average of all individual data values. So to find the mean, as I'm sure you learned in middle school, you add up all the values and you divide by the number of those values. So one way that we write it is like this: X bar is equal to the sum of data values over the number of data values. But sometimes you'll see it in either one of these two ways. So you'll have X1 plus X2. So those sub numbers, so like X sub 1, that just means it's the first number in your data set. 2 is the second number, etc. And when you see an n in any kind of mathematical definition, that just means the nth term. So if you have 20, n is 20. And then it's divided by n, which is the number of terms you have. And if it's 20, then you put 20 there. So another way to write it is this thing, this sigma, which you may have seen before. That just means add it all up. Add all the things. Sum it up. It's also called summation. It's a Greek letter. It's the capital sigma. So x sub I, that just means all the terms added up together over n, which we know about. So let's jump right into an example, and we're going to come back to this problem that we've looked at before, which is the number of goals scored in 20 games played by the 2016 U.S. women's soccer team. So here are all of our data points. So let's do two things. Let's calculate the mean. We're going to show our work, which is also one of my favorite things. And then we're going to talk about the mean and what we notice. But first, let's calculate the mean. And how we're going to do that is we're going to add up all of these values and divide by the number of values, which is 20, because they already told us. But if they didn't tell us, we could just count, and we'd find 20 of those. So what I've done is I've just added these up, and the great thing about the mean is that it doesn't have to be in numerical order of any kind, so I just sum it all up, and the total number of goals here, if I add them all up, is 63, going to divide by 20, because that's the number of data values that I have, and 63 divided by 20 gives us our mean, which is about 3.15 goals. So the second part to this problem asks us to take a look at the data that we've looked at before, and remember when we were talking about our dot plot here? And in that dot plot, we decided that 9 and 10 goals scored, those are outliers, because look at that. There's a big old gap between 6 and 8. So what would the mean be if we excluded these outliers? So what we're going to do is we're going to add up these values, excluding 9 and 10, and then divide by 18, because we're getting rid of 2 values. And let's see what happens. So I add up all of those 18 values, excluding 9 and 10, and I get 44, and I'm going to divide it by 18, because remember, we removed those 2 games, and that's about 2.44 goals on average per game if we excuse those outliers. We don't include them. So in comparison, if we include the outliers, we get about 0.71 more goals per average. So those 2 outliers increase the average. So a few more important pieces of information about the mean before we jump to the other measure of center. And we've talked about X bar, so that is actually the mean of a sample of a larger population. So that larger population's mean or average is something that we call mu. So that's a Greek letter spelled mu, pronounced mu, like the sound a cat makes. That's how it was explained to me many, many moons ago. So that would be the mean or the average of the entire population. And you would calculate it the same as X bar. You'd add up all the values of that entire population and divide by the number of values in that entire population. Something else about the mean is that it is sensitive to extreme values in a distribution. So take that example in the last slide. We had those 2 outliers, and it changed our mean by 0.7 if we added them or didn't add them into our X bar or our mean of the sample. So a word that's important here is something called resistant. So a statistical measure, mean included, is resistant if it isn't sensitive to extreme values. So I would say the mean is not resistant. Sorry, mean. So the other measure of center that we're going to talk about today is something called the median. Now, you've heard that word before, I'm sure. Think about the median on a road or a highway. It's something that splits that road straight down the middle. The median in statistical distribution is the same idea. So the median is the midpoint of a distribution. It's a number such that about half of the observations are smaller and half are larger. So it's smack dab in the middle. So if the number of data points that you have is odd, you pick the middle value. But if it's even, you average those two middle values. So let's try an example. Let's use that 2016 20 games played by the US women's soccer team, the goals scored. Let's find the median. Now, the thing here is that we first got to order these in increasing order or decreasing, don't matter, but we got to find that middle number. So order is important. So first thing I've done here is I've ordered my numbers from 1 to 10, and I cross them off as I go, so I make sure that I get all of them. And then I counted 9 in from the right and 9 in from the left, because remember we have 20 total games, so I'm not going to find an odd number smack dab in the middle. So I find 2 numbers in the middle, and I average them, and they're both 2, and the average of 2 plus 2, which is 4, divided by 2, is 2. You didn't need to do that to figure that out, but just in case you were curious. So our median, our middle number, is 2. So what happens when we compare the two measures of center here, the mean and the median? So we're going to organize these 3 ideas into the way that we talk about the distribution. So remember that we've got 2 main ideas here. We've got roughly symmetric, where there's a clear high point in the middle and then it kind of tapers off to both sides. We've got skewed to the left, where our tail is the thing that skews to the left, and skewed to the right, where the tail is the thing that skews to the right over here. So starting right here in the middle, roughly symmetric, the mean and the median seem to be the same in this example, the highway fuel economy. And the median is 22.4, and so is the mean. Interesting. So when it's roughly symmetric, our mean and median are roughly the same. So when it's skewed to the left, our mean is less than our median. So our median tends to be higher, and the mean is a little bit lower down here because that is skewed to the left, where our higher values are on the right-hand side. And then the opposite is true when we have skewed to the right. So that's when all of our biggest group of data over here is going to be to the left-hand side because the tail's to the right. So our mean is higher than our median. So 2 things to sum up those ideas is that the shape of comparing the mean and the median is that the mean is pulled in the direction of the long tail in a skewed distribution, right? So if it's skewed to the left, the mean is going to get pulled to the left. If it's skewed to the right, the mean is going to get pulled to the right. And then when we talk about outliers, the median is a resistant measure of center, while the mean, as we know, is not. So another way to sum all that up is this following color-coded chart that I will not apologize for. Gotta love color coding. So if a distribution of quantitative data is roughly symmetric and has no outliers, then that means the mean and the median will be similar. If the distribution is strongly skewed, the mean will be pulled in the direction of the skewness, but the median won't. So for right skewed distribution, the mean is going to be greater than the median. For left skewed distribution, we expect the mean to be less than the median. And as we know, the median is resistant to outliers, but the mean, oh, the poor mean isn't resistant to outliers. And that's going to do it for this video. Thanks so much for watching.